All right. Hopefully it's not sounded like I was a little too loud before. So this this talk should, by the time we finish, allow you to have a better understanding of how critical energy is. How important Wyoming is in the global energy picture, not just the U.S. energy picture. You will definitely have some understanding how energy usage has grown and, more importantly, changed over, say, the last 150 plus years. You will definitely at least hear many times that there are costs associated with all types of energy, and anybody that tells you differently is lying. The energy needs of our global 7 billion plus society will grow considerably, and the energy needs associated with that will be very significant. 5 billion and 7 billion people on Earth aspire to have the kind of lifestyle that we do. That's going to be a very significant challenge. And it's really not perfectly clear how we're going to meet these energy needs, but it's a really critical question. So if you look at this, what you can see, this is for U.S., but it's very similar when you look at for the globe. What you can see is that there have been very dramatic changes in the energy mix through time. What's really important is a couple of things. First, most important, is that gross domestic product, basically, which is a measure of our society, what we do, what we make, tracks almost one for one the growth in energy use. The fact that GDP growth is steeper than the growth in energy use is a good thing. It means that we're more efficient than we used to be. But we're going to talk more about this, but this gives a good summary of where we have been. We'll talk more about that. So the other thing that tracks energy growth, use of energy, is population. So in 1850, we were about 1 billion people using wood. So 150 plus years, 165 years later, we're 7 plus billion people. And you can see all these energy sources that have been layered on top of wood. Wood hasn't gone away, but biomass, but population, the existence of 7 billion people and increasing on Earth is directly a function of the amount of energy that we use globally. So, an overview of the global situation today out in the sort of near term is that energy use is going to increase. We will need more energy for a number of reasons that we'll touch on. And it's going to be a significant challenge to provide the amount of energy that we as a global society needs. And anybody that tells you that fossil fuels will not be a very significant part of the energy mix is either uninformed, lying, or something. You'll see that that is replacing fossil fuel completely tomorrow or over coming decades is going to be a very significant challenge. And out in 2030, most estimates are that fossil fuels will still make up around 80% of the global energy mix. And again, I will say this, and I will show you some things I hope document this. All energy types incur costs of many different kinds, and there are choices that we individually and as a global society can and must make regarding those varying costs. So if we look further out to the end of this century, and there's quite a bit of projection about the rest of this century. Beyond that, I have one slide that will go further. But again, fossil fuels are going to be important, but they will be declining in importance. All resources are finite, and there are going to be either new technologies or greater costs required to provide access to the energy resources and other resources. Earth's population has not stopped growing, and more importantly, a large part of the population aspires to the kind of lifestyle that we have that they see on televisions around the world. As we get later in the century, non-fossil fuels are going to have to be more and more important. Our lifestyle is going to have to change in some way. Either we're going to become much, much more efficient, which is hopefully possible. And as we'll look on a couple slides towards the end here, you know, there are some ugly scenarios that are posited in terms of what will happen if everybody on Earth, 7 billion plus people, 9 billion by the middle of the century, aspire to and try to have the same kind of lifestyle that we do today. So Wyoming, let's begin with Wyoming though and look at some detail in our state here. And Wyoming provides about 10% of the energy mix for the United States in total. And that was quite a bit higher just a few years ago. We'll talk about why that's changed. But what's really important perhaps from a citizen's perspective of the state of Wyoming is that 70% of the income comes from mineral resources, predominantly fossil fuels, so not entirely. So, and you're all aware that revenues have been declining, and it's a real challenge for the state of Wyoming. So Wyoming is a major energy producer. Essentially every major type of energy, Wyoming is a big player. Number 1, number 3, number 8, number 11. Wyoming is a very significant producer in all these varying energy types. And except for coal, they're pretty much all increasing in production as well. Maybe not natural gas at the moment either. So again, no other state in the Union derives more of its income than the state of Wyoming does from minerals, primarily energy types, various types of energy. So this is the state of Wyoming, the geologic map. And the reason I show this is because it's a good way to demonstrate where the energy comes from, where these energy resources are. This is a cross-section across the state of Wyoming. Jackson's there. So to the west, to the east here. And what you see are these big mountain uplifts, which is what most people come to Wyoming to see. And what's in between are these very deep basins with like 30,000 feet of sediments. That's the drive across part of Wyoming that people don't stop and want to see. But that's where essentially all of these energy resources, with the exception of wind, really come from. They come out of these sediments in these basins. So that drive across country is really, really important. It's where Wyoming's money comes from. So, some quick facts about energy in Wyoming. 40% of all the coal produced, mined, used in the United States comes from Wyoming, predominantly from the Powder River Basin. That's down, that 300 million tons last year is down by about a third since 2011. Most of the states in the Union receive coal from Wyoming. It's important in terms of natural gas. Our electricity primarily comes from burning coal. And as a result of that, we have almost the lowest cost of energy on an individual basis in the United States. So if you look back at 2010, you can see that Wyoming was the #2 energy producer, just a tad behind the state of Texas here. Nobody else is even close. If we jump ahead to 2014, what we see is Wyoming has lost about 10% of the BTUs that it was producing. Texas has really jumped way up there. Pennsylvania has become #2. And the reason for that really is the same in all cases here. It has to do with this. It has to do with technology, modern technology. It has to do with being able to drill horizontal wells and do hydraulic fracturing in rocks that just 10 or 15 years ago were not really considered a reservoir, a source of hydrocarbons. So that has changed many things, not just in the United States, but actually globally. It has had a major impact on global energy markets. So let's take a look at these one by one. And first of all, coal production is a heck of a big business in the state of Wyoming. Most of that coal, we produce most of the U.S.'s coal, and most of that comes, as we'll see in a moment, from the Powder River Basin. It's a result of unique geology. There was an inland sea from what is today the Gulf of Mexico all the way to the Arctic Ocean. And Wyoming was pretty low and pretty flat. And think of the Gulf Coast of the U.S. today. that kind of environment allowed deposition of tremendously thick coal deposits. And what's really critical is these are close to the surface. They're low in sulfur content. That's really important. Wyoming was not a major coal producer 30, 40 years ago until SO2 became an issue, sulfur dioxide. And per the Wyoming State Geologic Survey, Wyoming has approximately 20% of the global, at least recoverable coal reserves. So here, again, the state of Wyoming. Here are the coal basins. They are the same place as the basins in between the mountains. So the white spots are where the mountains are pretty much. And you can see that there's a coal field here, the Jackson coal field, just east of us in the Grovans. But it's a relatively minor resource, and it's hard to believe that'll ever be, anything will ever be done with that. But the Powder River Basin is up here in the northeast corner of the state, and that's where that 40% of the U.S. coal that is sold across the country comes from. The black is all the strippable coal deposits. These down here basically are burned in the Jim Bridger or the Naughton Power Plant. They are not shipped out of state. So, there are vast coal resources in this state, but the predominant, the really rich resource is up here in the Powder River Basin, extending up into Montana. It's a big business in every sense of the word, economically, physically, the resource-wise. Look at the thickness. I mean, this is one of these giant trucks. Look at the thickness of those coal seams. There are very few places in the world where there are coal seams that even begin to approach the thickness of what you find in the Powder River Basin here in Wyoming. So in every sense, this is a tremendously large business. For Wyoming, it employs a lot of people, but if you look at the coal business going back to 80, 90, 100 years, there's 10% or less, maybe 5% of the employment because we're using these things now instead of a pick and shovel underground in West Virginia. So, this is a little bit dated now, but what you can see, not surprisingly, again, as shown earlier, Wyoming is far and away the largest producer of coal. I mean, almost everything else, 40%, almost, it takes basically all the rest of the producing states in the country to exceed the amount of coal that's produced from Wyoming. These are individual mines in the Powder River Basin. You can see that they produce about as much coal as the second largest producing state here, the state of West Virginia. So it's a big business in every sense of the word. Coal production, as you're probably aware, you've been hiding in a cave somewhere if you're not aware, has really declined almost precipitously, say, over the last 9 or 10 years. And you can see that here. So you can see coal declining steadily. It probably has sort of plateaued at the moment, but it's gone way down. What you can see is that renewable energy has increased, but most dramatically, you can see that natural gas has taken off. And there is no war on coal unless it's an economic war. And the economy of using natural gas, which is incredibly cheap now, is the primary reason, along with the fact that natural gas is a much cleaner energy source than coal is. And you'll see momentarily what power companies are doing. They're not building coal plants. So gas and oil production has, 1884, it began over in the Wind River Basin just to the east of us here. That field at Dallas Dome is actually still producing. Wyoming is a very significant natural gas producer and has long been a significant oil producer. And you can see these are the fields of gas and oil across the state of Wyoming. And again, they're in the basins, not in the mountains here. And it's primarily gas, natural gas, to the southwestern half of the state. And for the green here, it's primarily oil in the northeastern part of the state. And I won't get into the geology of that beyond to saying that has to do with the nature of the source rock that was deposited. So something that many people don't realize is that Wyoming is the largest producer of uranium energy indirectly because we don't have any nuclear plants in the state of Wyoming. Everything is exported, but the state of Wyoming has the largest known uranium ore resource in the United States. And again, it's found almost entirely in these intermountain, intermontane basins. Wind is becoming increasingly significant, and per estimates that I've found, Wyoming has the 7th highest potential in terms of wind energy resources in the United States. Right now, when I had this data, we were about 10th in the country in terms of the amount actually being produced. In the year 2000, basically there was no wind energy production in the state of Wyoming, and that increased by 2 orders of magnitude by the year 2011, and it's still growing. And if you look at where the energy resources are, it's basically in the southeastern part of the state of Wyoming. Not surprisingly, mountains tend to block wind. You don't want to put a windmill out in the middle of the Green River Basin behind the mountains. This I-80 corridor, where the weather systems roar in from the Pacific, roar up the Snake River Plain and come through southern Wyoming, is the reason that all this potential, the blue and the red and then the pink, are the greatest areas of greatest wind energy potential. So when you drive across that I-80 corridor, that's why and that's where you see those giant wind turbine farms. And there's a project underway that I think has pretty much all of the permits it needs to develop a greater than 1,000 megawatt new wind farm down in the southeast a little bit of Rock Springs. So I think actually transmission capacity capabilities is the major holdup on the development of that major. That's an international scale type of project. So, we look at the key points about energy in Wyoming. It's a major factor player. It's really a global scale type of energy producer. It still is the 2nd largest producer by BTU basis of energy in the United States. We have constraints, though, based on power lines, pipelines, in terms of getting energy to market. And that is constraining to some extent further energy development in our state. Coal production, again, is declining. It has been for about a decade now. And that's primarily a result of the low cost and ready access to natural gas in our country. In Wyoming and other states, Montana in particular, keep looking to talk about trying to export to primarily China, but other places in Southeast Asia. They keep getting shut down by the state of Washington and other in Oregon. So due to politics and economics, I personally see that as quite a stretch to achieve. So let's now step back and take a look at the global energy picture, how we got where we are today, and maybe some possibilities about where we're going into the future here. And there have been really major changes in the production of energy, where our energy comes from over the last 150 or so years. And a key point I really want to emphasize is that these changes have taken decades. So we'll look at some data that help show and help explain that. You saw this right at the very beginning. Most of what we use is considered non-renewable energy sources, mostly fossil fuels. I should point out that what they label as hydro here is hydroelectric and all types of renewable energy other than wood, things like that. But what you can see is that there's pretty long times for a transition. You're not really transitioning so much as you're adding energy sources on top. You're layering them on top of what already exists here. And you can see hydroelectric and all the modern renewables are a very small part of that picture here. So this is where we have gotten to, and essentially how we've gotten here. Let's talk just a second about those transitions. And points that you should consider is that, as I showed there, and I'll show in another slide in just a moment, These things take time. They don't happen overnight. There are very good reasons why they don't happen overnight. Maybe the world is different today and in the future, but there's incredible amounts of money invested in infrastructure. Literally trillions of dollars invested in infrastructure around the world, and it takes a long time, and you really have to give people a good reason to replace that infrastructure. The economic, the social, the strategic reasons for doing so to change have to be really compelling. Otherwise, it's not likely to happen. And again, and I'll say this over and over and over again, always there are costs associated with any energy source, any type of energy, and many times we don't even understand, or most people don't understand what those costs are, what the trade-offs are, and that's something that I challenge all of us here to become much better educated about. They can be not just money, but environmental, social, political, strategic, and beyond that. This is a great graph that I found in Scientific American, a great chart a few years ago. It's time required for past global energy transitions. Down here is the year at which each one of these global energy sources became a key player at that, say, 5% threshold. So coal reached that 5% threshold in 1840, oil in 1915, and so forth. And you can see that it took 60 years for coal to reach a 50% share of the global energy market. Oil from 1915, it took 60 years to reach 40%. Natural gas in 1930 reached that threshold, and 55 years later, it's at 25%. That percentage is probably a little bit higher today, 27, 28, because of natural gas going up so much. Today, modern renewables are probably just at that 5% threshold today. 2012, they were not. So what does that tell us? The first thing I'll say is that the past is not the future. It does certainly not guarantee where we're going and what's going to happen. But I suggest that we would be very unwise to ignore what has happened in the past, how it has happened, and why it has happened. So again, these transitions took 50 plus years. So we're talking decades, and I will suggest, and most people do, that other changes going out in the future are not something that are going to happen overnight either. So today, if we look at and sort of move from today and into the future, I'm sort of done with the past now. I'd like for sure for everybody to understand how absolutely critical energy is to everything that we see and do, pretty much. Again, there would not be 7 billion plus people on the face of the earth. We would not have this highly advanced technological society. Pretty much, again, everything you see and touch would not be here without the access to the kind of energy and technology and other things as well. But energy underpins all of this. And again, every energy source has varying types of costs, and we need to understand what those are to make good decisions individually and as a society. And again, there will be challenges as we move in the future to provide the energy that we as a global society need. So here's a look at the global GDP and energy use, and you can see that GDP society has grown steadily from 1980 and on out in the future. What's really critical here, though, is taking a look at these two figures to your right, and you can see that energy use has declined as a function of gross domestic product unit. In other words, we've become more efficient, and that's an incredibly important thing that I'll show you more about here in just in a moment. So before I show further slides, I just want to make sure that everybody understands what the OECD is versus the non-OECD countries of the world. And so 2 billion people in the Organization of Economic Cooperation and Development, basically the rich club of the world, all the countries in dark blue here. And the other 5 billion people on Earth is everybody else, the non-OECD countries. So when we go to this next slide, what you see is that energy use going out in the future is probably going to be essentially close to flat for OECD countries. The growth is in the non-OECD countries. You can take a look at this, but I wanted to focus on this.
John, how much of that is China energy?
Save your questions to the end, and the next slide will answer that anyway,
Okay.
which is here. And that is, what, 2.3 or 4 billion people in China and India together, something like that, 2.2, 2.3. At least half of that is India and China. And again, if you look here, you can see that the OECD countries, the energy growth, use of energy is nearly flat. So that provides hope in a lot of ways as we look out into the future. But still, there's going to be tremendous growth in use of energy. These are the countries, these are the 5 billion people on Earth that aspire to the kind of lifestyle that we have. So if we look at world energy demand, you can look at it by where it goes, and we'll do a little bit of that more later. But let's look at here, which is where it comes from. And again, it's predominantly fossil fuels. But let's take a look at this in some detail and break this particular graph down. So here is that same graph. It's been squished this way a little bit. It's predominantly fossil fuels. What I want to do, this display really neatly shows, let's take this slice off the top, the renewables here, and expand it. What we see is that the bulk of that is what? Biomass and other. With other biomass is what? It's wood, it's dung, it's anything you can pick up and burn. That's what biomass is. And on top of that is hydroelectric and geothermal, primarily hydroelectric. And then on top of that is what we typically call, we think of when we talk about renewables, modern renewables, wind, solar, biofuels. So if we take this slice here and come over here and look at this, what we see is that most of that is biofuels. So ethanol from corn and all kinds of other things, sugar cane. We can see that the fastest growing parts of this slice, though, are wind and are solar here. But what you need to realize is that though these are growing very, very fast, far faster than any other energy type, they're starting from a very, very small slice of the energy mix, the global energy mix. And again, if you hark back to those earlier slides, these transitions take time for a lot of very understandable reasons. So to think that we're going to turn off all the coal, gas, and so forth fired energy plants around the world and be clean and happy tomorrow is, I think, not just unlikely, it's not going to happen. Not in a day or a week or even a decade or three. So here's another look, and this is from the EIA, the Energy Information Agency of the United States. Here, and what you can see is the recent past and their projections out in the future. And what you can see is that coal has been declining, continues to decline, though maybe it's flattening out in here. You can see that renewable energy is climbing very steeply. And there's a little bit of a plateau here, which we'll look at in a second. And look at what natural gas has done here. It's cheap and it's clean, so it's easy to access. So there are real reasons why it's replacing coal. Look at that inflection point there. That inflection point in 2023 has a good reason, and the reason is because the government subsidies that promote development of major wind farms across the country expires in 2023. So, and another way to look at it is this slide here, which again is from the EIA, and green is wind, yellow is solar, blue is natural gas, and black is coal. And zero line here, so anything below this zero line means you're taking it out of the system. Anything above that is an addition to the energy mix. Do you see any coal, black out here above the zero line to the right? No. What do you see? You see quite a bit of green here out to 2023. And beyond that, what do you see? You see a lot of gas and a lot of solar here. But no coal. It's coal-fired energy plants are only being removed from the system, at least per the predictions of the U.S. Energy Information Agency there. And this has some applicability globally as well. So every country has different politics and economic incentives that they do or don't provide. So again, I sort of hammer this, but I think it's one of the most important points that you may walk away from this presentation with, is that all energy sources have costs. All energy sources have costs. I'm not going to spend a lot of time talking about fossil fuels here because they're so well covered. I think most everybody realizes, CO2 into the atmosphere is a big deal. Pollution, of course, of varying kinds, mercury and other things from burning coal are can be very significant factors. But all other sources have costs too, and they can be financial. They can have to do with your allocation of resources that are available to you. They, of course, can be environmental. And critically, and not often thought about, is the dependence that they can bring on other peoples, companies, and countries here. That's one of the things that has changed so dramatically for the United States and a lot of other countries in the last, say, 10 years because of the growth of natural gas, primarily due to horizontal drilling and hydraulic fracturing. So, and again, many of these things are not well understood and by anybody that seems to talk about energy. So, this is there's some neat things in here. Wind, solar are restricted primarily to certain parts of the country. There are transportation issues. What I want to do here is focus on this particular graph. It's just a way to look at, I want to show you a couple of costs that people don't typically think about. And this is one, land disturbed per gigawatt hour. So what do we see here? If you really want to disturb not much land, you want to use nuclear or concentrating photovoltaic. Underground mining is pretty good, solar photovoltaic. The worst two from this particular metric are hydroelectric and wind. Reservoirs cover a pretty significant portion of the surface of the earth. And wind farms cover large areas, and there's infrastructure that's involved in setting them up. So I'm not trying to draw a judgment here. I'm just trying to give you the sense that there are costs that most people don't think about when they think about any energy source. Here's another way to look at pretty much that same thing, which is, in this case, they're turning it to how dense is the energy. And sort of flipping that last graph backwards, the most dense natural gas, coal, oil would be in there, nuclear, and the least dense energy-wise is solar and wind. So we're talking about 3 orders of magnitude difference here. This is something else that I came across in Scientific American a few years ago, and it's a really neat, little bitty short article. This is the extent of the writing. But what it says, and what it shows on the next slide, is that low carbon power depends on, as I say, climate unfriendly metals. In other words, it takes CO2 and other things that you spew into the atmosphere to create these metals, which are very important. So these metals are carbon culprits because they are produced in large amounts by high energy extracting and refining processes. Let's look at a display of that. And this is fairly dense, but I'll try and explain it here, hopefully fairly readily. The metals we're talking about are here, lower right, and from low to high greenhouse gas emissions. The current energy mix looks like this here. And so the current energy mix, this size circle here, the middle one, is the size of the energy, the metal associated with each of these energy types here. So if you want to replace something, let's say you want to replace natural gas with something else that's on this matrix here, how much of these metals does it require to do so, to put that energy source into production? So if you produce more natural gas than the current mix today, it uses, other than for iron, less of all of these metals. Not a surprise. And uranium is on here somewhere, I thought it was. Nuclear, right here. Well, you use more uranium. Surprise, that. But what's really interesting, and again, I'm not trying to judge, pass judgment here, but look at biomass. Well, look at wind. You require more molybdenum, nickel, a lot of copper in here. Less of some other things. Look at the biomasses, burning stuff like this here. There's a lot more of these metals required, and most interestingly of all, look at solar here. Again, I'm not trying to pass judgment or say what's good or what's bad. This is just another way to look at costs that are associated with using these various types of energy sources, and there are costs that people just don't think about. This is not one I had thought about before I came across this particular.
Is that a U.S. diagram or world?
U.S. This, as I recall, is U.S. Though the global energy mix is not that dramatically different either. So again, all energy sources have cost. I just want to repeat that and say this was a really neat view graph I got out of the Scientific American. So something different then. They all have costs of multiple kinds, but there is an energy source that is, I think without question, the very best one. And I asked what is it, I'm going to show you here right now. If you can figure it out from this graph, or this view graph here. This is a really interesting diagram that Lawrence Livermore National Laboratory has updated every year for quite a while now. And the United States so this is in the US, the United States uses nearly 100 quads of energy, and a quad is defined right here if you're interested in how many joules that is. So, but the thing is, since it's 100, basically, what we can say is that all these energy sources that go into our energy mix, those numbers are basically percentages. So petroleum is about 36% of the US energy mix. Coal, 14%, natural gas, around 26%, I think, or 25%. Solar is about 0.6% of the energy mix. There are a lot of things, you could talk for an hour about this slide, I'm not going to, but you can see some energy sources like natural gas are much more flexible than others. Petroleum, not surprisingly, primarily goes into transportation. You can see what goes into creating electricity. Coal almost exclusively goes there. But here is where energy is used in these four areas: residential, commercial, industrial, transportation. What I want to talk about, though, are these two things here, which are sort of cryptically labeled. And one is labeled as energy services and the other as rejected energy. What that means, if you translate it into common English, is this is energy that actually does work, that's useful work for us. It results in something that we want. This energy here, and look at how much of it is, it's two-thirds of the energy that we use, is energy that is lost in the system through inefficiencies. There is no perfectly efficient system. What this is telling you is that we're not as efficient as we could be, and we've become much more energy efficient, since 1980. But there's a lot of room here for improvement, particularly when you look at something like transportation, where maybe 20% of the energy is actually used to get your car down the road or the truck down the road. Fairly efficient actually is residential here, where over half is actually efficiently used to actually generate the lighting and or the heating that we need here. So, look at electricity, how much electricity is lost in either generation or transportation. The transmission lines are not particularly efficient. So there is a lot of room here for improving efficiency. And what I say is that energy not used is the only energy source, that's this here, which comes with close to zero environmental cost and usually a very low monetary cost. We'll explore that a little bit further, but efficiency is really important. You go back to mid-60s here, and we've increased efficiency by 25% or something like that. It's come down a long way in the intervening decades here, though maybe it's begun to plateau at least a little bit. That's a bit worrisome. But this is we'll look a little more at this. Without that increased efficiency, you could question whether we would actually be able to meet the energy needs of the world today without having become that much more efficient. So, by an IEA, which is International Energy Agency, not the U.S.'s EIA, they have some numbers here about how important, how big of a deal investment in energy efficiency is. We were talking hundreds of billions of dollars back in 2011, just in 11 major countries, and how this equals the total investment in electricity generation from fossil fuels, just a little bit less than investment in renewable electricity, plus the subsidies that go along with that. And by and large, this saves more, well, it does, it saves more emission than all the spending on renewables, and it pays for itself as well. So avoided energy is another term related to that, and it's the difference between the amount that we use today and the amount that we would have used if we had not become increasingly efficient. They talk about the amount since 1974. And that equals 2/3 of the global annual energy consumption. So it's a tremendous amount that we have saved by becoming more efficient. And it nearly equals the output of fossil fuels combined globally. So clearly, I think a best choice is greater energy efficiency and avoided energy use. But let's start to look out into the future now, and this gets into, certainly as we look further and further out, more and more speculative territory. But what does the future look like? And this is one view of the future. It's they term a business as usual scenario. You can see decline in petroleum oil production, significant increase in production of coal, particularly countries like China and India out in the future. Natural gas plays a very large role out in the future. And this includes growth in the global economy with some efficiency. You can see the curve is flattening out a little bit there. So this is sort of what we're doing today if we project it out into the future. At least this is their scenario out to the end of the century here. We'll see this again in a minute. So I ask you the question, we're asked this all the time, can renewables be the solution instead of those fossil fuels that we saw in that just prior graph here? And maybe. But what I would like to suggest is that it's not as easy as many people say every day in the news. I won't name names, but we hear it and see it all the time. We do know what the energy resources, what they are, and we know what the scope of them are. That's been studied, is being studied very well. So fossil fuels over here on your left, and renewables, of course, the big kahuna is the sun, which is actually also the source of all of this, if you go back in time as well. But we know what the potential resource is. But what's really key is to know what is usable, recoverable, at least as we can with the technologies we have today. So these are not unknowns. That doesn't mean that things can't change. If you look at natural gas, for instance, predicting that we were going to grow the amount of natural gas produced the way we have over the last decade, 20 years ago, people would have said you're crazy if you had predicted that. So technology can change things. That's possible. So if we're going to do what some people say we need to do, which is decrease the amount of CO2 being put into the air, this particular study posits that we need to decrease fossil fuel use by 2.7% a year, that's this, and increase carbonless energies, which includes nuclear, by 5% a year. And again, they're showing a very steep growth in energy use out in the future, so that's part of their scenario here. So the question is that realistic? And I don't have an answer, but I will give you some data that provides some things to think about. This is the, as not long ago, the contribution of the global energy mix by various renewables, and you can see that, not surprisingly, the majority of it is biomass and hydroelectricity. So the question becomes, for these other renewable energy sources, can one or more of these make a dramatic change, a significant change to the energy mix as we go forward? So I'm going to pick one. I picked wind because it is a big one. Here it's a very significant one. And I found this neat graph which shows the amount of wind energy generation capacity that was added each year from 1996 out to not that long ago here. And the wind energy has been growing by these data points here in the 20 to 40% range for a fair length of time. And so the question is, can we continue that? Well, here is some, again, very interesting historical data. And what these data show is that it's the 10-year running average of the growth rate of these various energy sources, and basically no major energy source has maintained a growth rate of over 10% for 50 years. Basically, as soon as an energy source becomes quote-unquote mature, a mature energy source, its annual growth rate, and we see that in the historical data, falls below 5%. So what does that tell us? I would suggest that it suggests that a sustained dramatic growth is at least unlikely. Can't say it's impossible, it's unlikely. And if you take that average line from that previous graph of wind growth, or the growth in wind energy production, you see how it falls on this slide here. And I added this, and I think it shows it's pretty interesting. It looks like a lot of these other things do early in their contribution to the global energy mix as well. And a reason for that, at least a partial reason, is certainly that the easiest things, the cheapest things to do are always the things that are done first. So if you're going to build a wind farm in Wyoming, you're not going to put it in the middle of the Green River Basin. You're going to put it on top of some of these ridges along that I-80 corridor. And there are only so many of those places that exist. So those are the ones that are utilized first. So we already looked at this. I'm not going to go through this again, but I will ask, I guess, if you think the world is different now. And I don't know. Unlike these past energy transitions, maybe there is a moral imperative to change what we do, an existential imperative. So maybe we will choose as a society to pay for the cost of using alternative energy sources, as opposed to letting pure economics dictate what happens. And certainly technology can and does make a difference. And the cost of the various energy sources, renewables, has declined significantly as a result of technological change. So, the challenge to meet future energy needs is big. We're going to get into some really arm-waving stuff here. This is a neat graph. So, 14,000 years of positive human history here, if we last that long, out to the year 10,000. What's really neat about this is from a guy at UC San Diego. And you can look this up, and there's a lot more neat stuff, I think, on his website. But he's trying to put some perspective on this. The period of fossil fuel use mirrors one for one on this side, on the left side at least, the growth in human population and the growth in our technological society, high technological society. So we're somewhere on this side of it here. We're going to reach some peak up here. And we're going to want to be producing energy at least at that same rate on out into the future to maintain our lifestyles. And so his question is twofold. Is there a way to fill this? And secondly, if our global society has been so dependent, and the population growth as well, on that direct tie basically with fossil fuels, can we change that? That's a very good question. He's not providing an answer, but it's a very good question to have all of us think about. So there are a lot of gloom and doom and the world is happy scenarios, and here's one of the gloom and doom ones. It's a little bit dated, but it's a sort of a neat graphic here. You know, they say we reached the sweet spot back in, I don't know, 1980, 85 or something like that. Population, resources, food, and everything else, you know, that was sort of the peak. We're going to see resources decline. We're going to reach a peak out here somewhere a couple decades out. And then things are not going to be so good after that, according to, and there's a lot of stuff like this if you look on the internet out there about you know, very much gloom and doom types of scenarios for the future. This one is maybe sort of some gloom, some doom. You can see what their predictions for the future are. You know, a lot of renewables out here, but you know, they see sort of a, you know, just sort of a decline, but nothing precipitous here. Then there are people that say, don't worry, you know, be happy. There's all kinds of resources out there, and one of those, as some people tout, is oil shales here, and they're saying that all these fossil fuels can be replaced with billions of barrels of oil shale. And I'll give you one slide on that here, a lot of words, but there's basically about 4.5 trillion barrels of potential resource in southwestern Wyoming, northwestern Colorado, and northeastern Utah. It's not oil, it's not gas, it's kerogen in the rock, which is a precursor for oil. But if you take the richer parts of those rocks and cook them at a pretty high temperature here, you'll get oil out of those. And there have been companies that have been trying to make this economic for over 100 years. And I guess what I would say about this is there are companies that have been trying to make this work for 100 years, and they're still trying to make it work economically. Technically, it works. Technically, it's certainly possible. But the environmental cost, the amount of water that's required to do it, the amount of energy that goes into it, make it really something that I think is highly unlikely, but it's a heck of a big resource. There's a difference between resource and reserve, something that you actually can use. So there are other things out here. This is one that really has taken off. And if you go back to somewhere back in here, the early part of this century, there is nobody, I would suggest, that would have predicted that we would see these kinds of natural gas resources be available. So things can change. And you know, these are pretty reasonable projections about what might be available as we go out in the future. And certainly, natural gas from these non-traditional resources are going to be a very important part of the picture. Similarly, from rocks that were not considered resources for oil production, there are similar things being done today. And again, you can see that very likely oil production will be very significantly increased as a result of these new technologies, horizontal drilling and hydraulic fracturing. You know, probably every significant government in the world and many other bodies as well, non-government organizations and so forth, are thinking about these kinds of things. Maybe not everybody we'd like to see thinking about them is, but there are very significant parts of our global society that recognize this as a challenge and are thinking about these issues and are considering the challenges that are out there. So here's the German Government Advisory Board. And what they say is by 2100, basically, Germany's going to provide most of its energy from solar power, which I think is very brave, given that Germany is probably, Northern Europe is not exactly the sun capital of the world, as I understand it. And when you look into their reports, it's really hard to understand. They don't really provide a lot of specifics about how they're going to get there. But they are putting a lot of energy into wind and into solar energy, a lot of effort into it, I guess I should say. So there's one answer. And if Germany can do this, well, then Greenland can do it too, and Canada can do it. We're set. This is something from a Russian government agency here, and what you can see, this agency in Russia is positing is that renewables are going to have to be a very large part of the answer as we go out to the end of the century here. And so basically what this report says is we need to work on this, and we need to work on it right now. Now, I haven't seen anything that suggests that Vladimir Putin is a big subscriber to this, but at least some parts of the Russian government are clearly thinking about this. This comes from the Netherlands, and you had seen this graph earlier. Here is an alternative scenario that they put out, and you can see that renewables are a significant part as they go out in the future. You can see that this is much more efficient. They're saying we will be much more efficient than we are predicting in this particular scenario. And what they're using here is something called carbon capture and storage with a lot of fossil fuels, but you're not pumping CO2 and other nasty things into the air. So, basically they're saying we need to use all of these here if we're going to solve the need that our global society has and the individual country has as we go out into the future. So, sort of my summary, or almost my summary, is that if we're not doomed, if the doomsayers are wrong, and let's all hope they are, then almost certainly some combination of all of these energy sources in some mix with some new technologies are going to need to be part of the answer as we go out into the future. And this last, the previous graph is perhaps one that offers a most likely, in my estimation, type of possible scenario as we go out to the end of the century. So, by conclusion, in the shorter term here, energy is important. It's critical. There is no way that our global society works without the amount of energy that we have available to us. Wyoming is a very important part, not only nationally, but even internationally on this global energy mix. Economic progress, especially in developing countries, will drive global demand higher. There's no way to avoid that. Even if we get better and better in terms of efficiency. And again, remember the non-OECD countries, 5 billion people on this planet that aspire to the same kind of lifestyle that you and I enjoy, and that's likely to be about 9 billion people by the time we get to the year 2050, or the estimates that I've seen. Fossil fuels are going to be a very important part of this, particularly looking out in the nearer term, say to 2030 or so. Again, every energy source, including renewables, have significant types of cost of varying kind, not just dollars and cents. And again, the very best new energy source is actually greater efficiency. That's certainly, it has to be an important part as we move forward. So if we look longer term, say out to the end of this century that we're all now in, there's no doubt that economic progress will remain intimately linked to the availability and use of energy. There are limits. We don't necessarily know exactly what they are. Technology will play a key role in establishing what those limits are, but there are very significant unknowns for the future, and we have to be prepared to deal with those. The past isn't the future, but you've seen a lot of data from the past that I think should give you reason to think perhaps differently about what the future might hold. And at least I think it might cause you to question somebody who gets on whatever news service you like to listen or watch and says, we just need to do this and we're going to solve everything tomorrow. Again, no names shall be cited. So by conclusion here, we're going to have to find more energy, produce more energy. You can't predict the future with certainty, and there are multiple scary scenarios out there. You can find a wealth of them, more than you want to read in a week or 3. So I'll suggest that it behooves each of us, our nation, and our global society to explore all of the various possible ways to solve the energy needs for the future, and to do that now, as some people are. So I will just leave you with this thought. that would be a great idea for all of us to learn as much as we can, both individually and globally, and to make good decisions. Thank you. There first.
Well, thank you. I think it's very informative. I've got two questions. An observation and a comment. The questions are, why, if the government's going to pull the plug on subsidizing this fantasy we have of wind energy, do we continue to pursue it? The other question is, what is the percentage of nuclear power that France uses? The observation is that you've only mentioned nuclear one or two times. You've shown it in the graph, but you saw a precipitous drop in nuclear. And I guess the comment is, I think we're all being delusional when we don't, and afraid for the wrong reasons that we don't go after nuclear power. And not once, you didn't seem to support it or push it, or you don't want any conflict in this room. But I think in this world of technology, which the United States is using, we're number one, we can figure out what to do with the spent uranium, providing we don't have people in our government who are selling somewhere with uranium to the Russians.
I will respond by saying that you saw that basically the concluding slide that I propose. I suggest that we need to consider all energy sources to reach a really reasonable and rational solution for our future needs. I'll turn around and say it wasn't so much a question you posed as a position, and I understand that. And yes, France produces, it was right at 90% of their electricity used through nuclear. It's far greater than any other country on Earth. And we're all well aware of the concerns about nuclear, Chernobyl, Fukushima. So there are it's a decision that we as a society have to make. And it's also not cheap. Nuclear energy is not by any means a cheap per kilowatt hour energy source. Part of that is regulatory, but part of it also is technical. So, Peter, I don't know if that, anyway.
John, you're looking at the efficiency gains that can happen over the next 25 years.
You want me to predict the future now?
Well, no, I'm asking your opinion. If you look at what happened in the 25% efficiency gains from the 60s to today.
Yep.
What do you see? Can you just talk about some of the things you see as the areas of opportunity to take another 25% chunk from efficiency?
Specifics. You can look at what's happening in each of these energy sources, industries really, wind, solar. You pick at nuclear, fossil fuels, and there are changes that are happening. I cannot say with certainty what's going to happen in the future. You saw in that one graph that things appear to maybe plateaued a little bit in terms of increasing energy efficiency. I guess I would answer by saying that I think there will be increases in efficiency. Certainly, photovoltaics, as a good, for example, are 4 or 5 at least times more efficient than they were 10, 15, certainly 20 years ago. So I think there will be, I think there has to be increasing efficiency, and I think there are a lot of organizations that, government and non-government, and the industry that are trying to achieve that. If nothing else, if you're in an energy business, you make more money if you make it more efficient. So there are real drivers in many firms to make things more efficient than they are today. So I think they will become more efficient. Bob?
You hit on my favorite subject, efficiency. There are certain physical limits to the efficiency that you can achieve by any of the systems that you want to develop energy.
Absolutely.
Let's take photovoltaic. I think the physics limit is something up in the 30% range. I'm not sure.
Which we're not close to.
No, we're at
10.
Actually, the top stuff that you stick up in space because it's so expensive to get there is near 20%.
Yeah, once you buy those,
But the
8 or
stuff
10.
you buy from China now, all this stuff is coming from China, is 10, 11%.
Yeah.
300 watts per square meter or solar panel. Okay, what's the boiler efficiency of all our power plants? The least efficient is natural gas. Next efficient would be oil and coal from kind of time. Oh, excuse me, least efficient is nuclear. But actually, if you take gas and burn it in a boiler, first don't burn it in the boiler, use the combined cycle generation, you can get a total combined cycle efficiency up in the 40% range, which is really good. So you cut down on your waste heat. And just to make a big jump here, I see from the first slide and then your last slides, I see a tremendous collision between population and lifestyle versus energy availability. One of the biggest factors here that could affect is population. If
Not just increasing population, but more the desire of the existing population
Yeah.
to live like we do.
actually, this physical population, if the physical population were to decrease dramatically, then it would change the whole scenario. And when you're looking at the questions, as you say, very carefully look at all the parameters. There are trade-offs all across the board. And you have to look at from the input to the output to the trash. What does it cost you? And when I say cost, don't look at dollar signs. Look at all the other costs, the social costs and everything, the environmental costs of producing energy. It's very complicated and lots of people just gloss right over it. When you look at the 6 o'clock news, they don't care about this.
That's next year or 90 years from now, so why should we
If you
care?
want to take all these points that you've got here and spend 2 or 3 days, you can look at every item and then look at the input, the output, the social costs, all these other things. And politics is another big cost.
Absolutely, absolutely. There's a wealth of data out here. What I've tried to do is give you a tour,
Okay.
a sample of what's out there, sort of, you know, the highlights, if you will. But there were a couple of points I really wanted to hit on. One is that everything has costs, and you know, there's a lot of uncertainty about the future as well. So yeah, your points are well taken. So let's go here, there, and then there. So,
John,
so speak up.
yeah, your graph that showed the efficiency in transmission is an excellent graph.
You can find that's Lawrence Livermore produces that annually. You can go back and look at versions going back.
Because in transmission, there can be greater savings with direct current
DC as opposed to AC.
instead of AC, and also cryogenic transmission, which is a technology we need to develop. It would be a huge savings.
DC is actually becoming the choice for long-distance transmission globally, actually. The Chinese are at the forefront of developing direct current transmission systems. It's much more efficient than AC. So back there.
Hi, I was just wondering if anybody under 30 can stand up.
Yay!
Awesome. So
I'm still standing.
Where do you think they are?
Okay. Well, I just want to say that all these decisions are going to impact people my age and around my generation for a lot longer. And I think it's really important that we're including younger generations in this discussion. So I was curious what you're doing to incorporate younger people in these sorts of presentations.
What I am doing? I'm going to support my grandchildren going to university when they get there. I'm, trying to keep abreast of things like this and give presentations. I give this presentation. I have been giving it down at Camp Davis, University of Michigan's field station down here for the past, 4 summers, and we'll do so again this summer. Those kids.
And the community school?
Well, yeah, it's a community school, but so education, I think, in my estimation, is one of the most important things that I can do and encourage people to learn, because I think most people, even in this highly educated community that is Jackson Hole, aren't really terribly conversant with most of these issues. There was somebody up here, wasn't there? Oh, Hal.
My question basically was about modernizing our power grid and what kind of efficiency and savings. It was already basically covered, so good comments.
Yeah, DC transmission is clearly the way to go. to change, if we go back to that Lawrence Livermore, I don't know if I can, how fast I can go back to that. That's a really neat, I go too far. Oh, I'm going the wrong way. Sorry, I'm going into all the extra slides, all the garbage that we don't need to go into all that stuff. But now I'm going the right way, and we're talking about still further back, Lawrence Livermore. Further back. There it is. That's a really neat slide, and I would encourage you to go to Lawrence Livermore Lab's website, or if you just type in Lawrence Livermore National Laboratory estimated U.S. energy use, this will pop up at the top of the search engine here. And this is a view graph that's well worth spending quite a bit of time looking at, thinking about, and understanding. And actually, one thing you will find if you look at the older versions, and I have some further down, we're not going to go there. If you look back at, say, the 2011 version of this, you'll see that the rejected energy is actually less a percentage of the energy mix than it is in 2016. And that has to do with some of the choices that we as a country have intelligently or not made with respect to how we're producing our energy. So those are data. Those are not projections into the future. Elizabeth.
I'd like to reply. The geologists of Jackson Hole reach out to all the local school districts and go to the schools and individually talk to different classes whenever we're invited to go. This program and others are up on YouTube for anybody who cares to just tune into Geologists of Jackson Hole, and so it's available. But we do need somebody to head up our juniors program, and if you would like to be that person, we talk fairly frequently about how many gray heads there are, although not me. And we need somebody to help us attract people of a younger generation. It's in the paper for everybody to see. It's not that we're closing the doors. So if you have good ideas to help us bring science to a younger generation, we'd love to hear it.
Yes.
Okay?
Yeah.
I think this is a hot button with white hits. I think this school district here is really quite aggressive, and this woman that says superintendent of our school district here, Gillian Chapman, is really receptive to this kind of thing. And I think there's opportunity to speak in an auditorium setting at the high school, for instance. Somebody just has to approach Gillian and bring up the fact that you'd be the perfect one to do it. But I think it's nice that you ask, and I don't think also that when I was your age, I'm 78, when I was your age, I really cared. Matter of fact, I'll tell you.
It's different today.
So I think it's great that you're much better educated than I was at the time, I'm sure, and that you're interested in it. So that's nice of you to make your comments.
Any other questions, comments?
Now, you have a number of slides that showed projections of various uses of energy. Without exception, fossil fuels were all going to be declining in some cases.
There was one that the business as usual one posits that coal will expand greatly still, but that's probably not true anymore. I think.
Got into specific countries, clearly their projections were declining. I guess my question, one we might not be able to answer, is that because, quote, there's a lack of fossil fuels, or is it because someone has made a predetermination, politically or otherwise, that one should not be using fossil fuels?
I think it's multiple reasons. There are good reasons why 15 years ago nobody would have predicted that natural gas would be so abundant and so bloody cheap as it is today. That there was a technological change that really has impacted the global energy market. It's impacted us on an individual basis as well as an international basis. So, but there are limits. I mean, there are reasons, there are very good reasons why Chevron, Exxon, Shell, and so forth are drilling wells out in 10,000 plus feet of water today in the Gulf of Mexico. If there were vast, easily accessed or accessible resources of oil onshore, again, there's some tight rocks that we're accessing now that weren't considered a resource in the past. Yeah, but there is a finite limit, and more importantly, there's an economic limit, even more than a resource limit to what's out there and what's available. There are, of course, political and social choices that we, maybe not you, not me, but us as a global society are making in terms of, we look at the Paris Climate Agreement Accords. For better or for worse, depending on your perspective, those are decisions that we as a global society are making. And those are also certainly a factor in, I think, a lot of the predictions of decline in fossil fuel use. But nobody, barring one or two organizations who I will not cite, are saying we should turn off all the fossil fuel power plants tomorrow. We can't do that. Your lifestyle, my lifestyle depends on it. It's not going to happen. But there are good reasons behind all of those various predictions, those guesses about what the future might look like. And we can see what those factors are as we look around us today. We talked about them a little bit here. So, there's 4.5 trillion barrels of oil shale right down here south of us, but that's probably not the answer.
40 years ago, when I was getting my master's degree in environmental education, there was a saying called, "There's no such thing as a free lunch," and that is exactly what our society is facing. Since it's not a free lunch, there are trade-offs, and we have to make those in an intelligent way, whether it's pollution versus cheaper energy or whatever. There's no such thing as a free lunch.
I didn't say it quite that way, but that's what I'm saying. There is a cost to any choice that we make. So